what I'm going to call the beginning of real physics for the year. What we did in chapter 1 was science, right? Science, the concept of estimations, dimensional analysis, you did in chemistry already. So this is the first real physics we're going to start for the year. And even in this section, or the first 3 sections, you'll notice, when we look ahead, that a lot of this is also part of what you learned in freshman year, in your Algebra 2 or for all of you, Algebra 2 honors course, with distance rate problems. You'll see a lot of similarities to distance rate problems in this section. Okay? So we're going to do 4 main things here. We're going to describe motion in terms of 3 things. We'll talk about a frame of reference. We'll talk about displacement, time, and velocity. 4 things. Calculate the displacement of things in a time interval given. And again, that's got to be at a known velocity. We'll construct and interpret graphs, something we kind of looked at already from the lab. And then we're going to talk about average and instantaneous velocity. So let's jump right in. So the first term we're going to look at today is called reference frame or frame of reference. Reference frame or frame of reference. The idea here is that our current location, placement in time and space matters. It matters a lot. Like right now, what would you say my velocity is? Okay, and that's with respect to what surface? The floor. Is that reasonable to say? Okay. Now, with respect to the universe, what could you say my velocity would be? Anybody know the speed at which the Earth rotates? That's what's that doing. Right, the Earth is rotating, right? So with respect to the universe, I'm moving right now in circular motion with what we're going to call later on tangential velocity. So right now my speed is around 23,000 miles per hour actually, with respect to the universe. But the Earth is sucking me toward its center with gravity, so I'm not getting launched off the surface, which I would if the Earth weren't pulling me toward the center. So my frame of reference matters. A simple example, that one is probably a little more difficult to perceive because we can't really perceive outside the universe unless we're astronauts in space. The easier one to think about is motion on a moving object already. When you get on the subway, when you're on the subway and you're standing there, right? And you look out the subway, and there's a subway car next to you. And it looks like the people next to you are just kind of cruising along. It doesn't look like they're moving. It doesn't look like you're moving if you're both moving at the same speed. But if they're moving a little faster than you, when you look out that window, you see them going by like this, right? You ever wave at people like that? You ever do that? You should do it sometime. We're never going to see them again. Do it next time. It's kind of weird, but just wave. Now, or you can start tossing an object up and down like a physics person, like, what's happening? The object's moving with me. It's your inertial reference frame, whatever. So when you're moving though in the train, if you were to start to walk in the train, your actual velocity would really be the sum of your velocity and the train's velocity. Think about that for a second. If the velocity is traveling, if the velocity of the train, and the train is traveling at 20 miles an hour, and you decide you're going to get up and just sprint to the front of the train, something happens, somebody's smelling in the back of the train you got to go away from. So you sprint toward the front of the train, you get to the front of the train. As you're moving, your velocity is 30 miles an hour, plus, let's say you're sprinting at 15 miles an hour, you're a pretty good sprinter. So your velocity really is 45 miles an hour with respect to the train tracks or the platform that you're passing. Say you're passing, 51st Street on the express train going downtown. Your velocity is the sum of those 2 velocities because now you're comparing your velocity to the platform. Well, you got the train and you moving together. What if the train is moving 30 miles an hour this way, but you're moving 5 miles an hour this way? Then what does it feel like you're moving actually with respect to the nearby surroundings? Be 25. Because again, you're moving the train's moving 30, but you're going against the motion of the train at 5. So if somebody were outside the train watching you, they would see, you're moving this way, walking, but your body would still be going that way compared to where they are. Because the train's velocity is greater than yours backward. If your velocity could technically be greater than the train, you'd be moving backwards actually. But it's not going to happen anytime soon. Yeah?
So if you're on a treadmill, is your velocity 0?
Say again?
If you're on a treadmill, sprinting.
It depends on what you're relative to. Relative to the treadmill surface itself, you have velocity. Relative to the ground next to you, you have 0 velocity. So your frame of reference is what changes there. if I'm considering the treadmill to be the frame of reference, then I'm technically moving with respect to the conveyor belt itself. I have a velocity of 10 miles an hour. But compared to the floor next to me, have I moved at all? No. I'm literally in the same spot compared to your little brother or sister watching on the treadmill. You haven't physically moved. So it's always with respect to that matters. Okay, your velocity with respect to is what matters. Okay, let's take a look at this next terminology here, displacement. So the concept of displacement is very much like what you did in the lab on the roof on Thursday. And the idea here is that your displacement is a change in your position. Your position. Now, we are going to call our current position in all terms of physics, we're simply going to call that x. So maybe put an arrow here and label that current position. x0 is going to be called our starting position. Another phrase for this, which is widely used in college, so get used to it. x0, another phrase is x0. N-A-U-G-H-T. x0. Another phrase meaning zero, not, nothing, zero. So your current position is denoted by x. Your initial position is denoted by x0 or x0. And your actual displacement is the change that occurs. In Greek, change is symbolized by what symbol? Delta. So we see delta x, or the change in your position, that's your displacement. This symbol means displacement, delta x. Okay, and displacement by definition is the change in your position. Now, something to write down. This is one of our notes that is not on here, but you should note to yourself. Displacement is a vector quantity. We're not going to get into vectors too much yet. We will in the next chapter, in chapter 3. But I want to mention this now. A vector quantity has a magnitude. Another word for magnitude is value, if you want to put parentheses. And a direction. Again, a vector quantity has a magnitude and a direction. Another word for magnitude is value. Value. Quantity. Those are fine. So, what do I mean by that? If displacement is a vector quantity, by moving to the right, what kind of displacement would you consider me having? Good. But Isabella, if I move to the left, what kind of displacement do I have? Negative. So the vector quantity here simply indicates that direction matters. So what are we going to say in general? God bless you. We are going to use our xy axis, our traditional Cartesian coordinate system, as our denotation. So on the Cartesian coordinate system, this way is positive, this way is negative. Agreed? I'm making an xy axis right now. And then this is positive and this is negative. We've always accepted that. We could change it today. And you know what? When I was in high school, my AP physics teacher, and when I was a senior, the second time I took physics, actually for the first 2 weeks of school, just to mess with us, to prove a point that it doesn't matter what direction you choose, as long as you're consistent, he made everything up negative and down positive, and left positive and right negative. For the entire first week or 2 weeks of school, just to change our mind thought, or our mindset, or our thought process. I'm not going to do that in the first week because we haven't adopted a thought process yet. But maybe next year, if you have me for AP Physics, I might do something like that, where it's going to think differently each time. Okay, but we are going to adopt the notion that right is positive, left is negative, up is positive, down is negative. Okay, if you have a question, just stop me. I'm not always going to say any questions because I want to continue the class and keep moving along. So let's look at our first example, a very simple one. We can talk through this together. No need to do it individually, it's not a lot of math. A space shuttle takes off from Florida, encircles the Earth several times, finally lands in California. While the shuttle is in flight, a photographer flies from Florida to California to take pictures of the astronauts when they step off the shuttle. Who undergoes the larger displacement? Who undergoes the larger displacement? So by who we mean the astronauts or the photographer in this case, right? The astronauts or the photographer. Mr. Genesi, what are you thinking?
Well, I would think that the astronauts would, because they're going around the Earth multiple times.
And landing in California?
Yeah.
Whereas the photographer is doing what?
Just going from Florida.
Okay. I like the idea and the logic behind what you're thinking. Want to help me out?
Would it be the same?
It might be the same though. That might be an idea to think about. George, why might be the same?
Because given it's just your current location and the starting location, those are the same for both of them.
So that's right. What did Jack refer to then? Help Jack out there. What was he referring to when he said one was much larger than the other? Was it displacement? Distance traveled. So that's a really good point, and it's okay that you made that thought in the first time through. But now we write a note down. Displacement in this problem is the same. They both start in Florida. They both end in California. But the distance traveled in this problem is not the same. Sometimes they will be the same, and we'll discuss that in a moment. Again, the distance traveled for these two scenarios, or these two movers, the astronaut and the photographer, these two objects in motion, the distance traveled are not the same. Are not the same. So the astronauts clearly travel a much longer distance because they circumnavigate the Earth several times, okay, before landing in California. Now, the idea of distance and displacement is really, really important, and we're going to keep going with this for the next example, okay? So let's go right into the next example. So example 1, you would consider on one of my tests a theoretical example or a short answer. On my test, to give you a format, because we're talking about these problems, I have multiple choice, I have what I call short answer, and what I call mathematical. This would be categorized as a short answer. If there were choices, it would be a multiple choice, obviously. Multiple choice can be math-based or theory-based. But your short answer are mainly going to be theory, and your longer answer are your mathematical problems. So this would be a short answer. The next one would be a mathematical one. It looks lengthy, it's just really wordy. Okay, it's just really wordy. It's not a tough problem. Can I get a reader to read it nice and loud for us? Go ahead, Christina.
Your office, the deli, the subway station, and the nearest electronics store are located at the following positions, respectively. X1, 20 meters, X2 equals 240 meters, X3 equals 140 meters, X4 equals 280 meters. You arrive at work in the morning, and from that point on, you do the following. Leave the office and go to the electronics store for a new pair of headphones at
Oh, Nora, sorry, title. Go ahead.
Then go to lunch at the deli. Next, you head back to the electronics store for an adapter to connect your headphones to your phone. And finally, walk to the subway station to take the train downtown for a meeting. At this moment, waiting at the subway station, what are the values of your distance traveled and displacement?
So what might be useful, thank you, Christina, for a problem like this to start? Just to start it, what do you think might be useful?
Draw a photo.
A diagram would be really nice for here, really useful here, or very nice here. The reason being is it's very wordy. You notice that? A problem like this? On a physics SAT subject test or AP exam, at times wordy problems can get confusing. So a diagram is very, very useful. Caroline?
I have a question just about like the structures of problems.
Yeah.
So it asks, it says you arrive at work in the morning. Did you get off the subway?
Well, read what it says. You arrive at work in the morning, and from that point you do the following. Leave the office. So where must you start the problem?
The office.
At the office. Yeah, that's okay. And it's purposely written this way because you want to, in physics, recognize where a problem begins and ends. Let's write that down, actually. It's really important to denote when the problem begins and ends. We're going to have problems this year that are really complex, and we're going to have to break them into 4 or 5 parts. So I might call the first part like part A, where like the person leaves the office and goes somewhere else and does something. Then part B, maybe they leave the store and go somewhere else, and that involves friction, so I have to make it a new part of the problem. So throughout the year, we're going to what's called truncate or break up a problem into important parts. So it's really important to recognize where it begins. So in this problem, you begin at the office. So a diagram would be useful. You can start drawing a diagram if you want, but keep in mind where your locations are respectively. Okay, the office is at 20, the deli is at 240, the subway is at 140, and the electronics store is at 280. Respectively means in the order it was given in the problem is the order of the locations x1 through 4.
Do the distances mean like from your home?
So again, it just says, at this moment, from waiting at the subway, what are the values of the distance traveled and the displacement? So from the office, doing all that stuff, ending at the subway, what was your total distance traveled and what was your displacement? So from the office,
But do they mean like the 20 meters, does that mean 20 meters from your home, or does that mean like?
it means somewhere on the x-axis. Let me draw a diagram to help
Oh,
us.
okay, so this is subtracting.
Yeah, so this problem, again, whenever you're given x values as positions, I want you to start thinking about a number line. Right now, we're only doing one-dimensional motion, so everything's going to be only along the x-axis or along the y-axis. Later in chapter 3, we're going to look at projectiles that are launched at angles, and they move both in the x and the y direction. Here, I'm thinking about this as flat land. So I've got the office right here at 20. At 240, I've got the deli. At 280, I've got the electronics store. And then here at 140, I've got the subway. So that would be my diagram for a problem like this. Do I care about numbering every other number? No, this is not 6th grade math where you number everything on a number line. Don't waste time. On physics exams, you're going to notice, because it's a critical thinking exam, that you will lose time thinking about an answer. Don't lose time adding extra stuff along the way. So I only denoted those 4 locations. I then read through the problem. As I read through it, let's denote with colors. So the first part says, you leave the office, and you go to the electronics store. So here's our first denotion right there. That's our first path. Okay, leaving the office and going to the electronics store. The second one in blue, you then go to lunch at the deli. Well, you're at the electronics store. You can't just teleport. So you're starting at the electronics store now, and you're going to the deli. Then it says, next you head back to the electronics store because you forgot that adapter on that stupid new iPhone that doesn't have an auxiliary port for some crazy reason. Does the new one have it or no? Anyone know? The iPhone 11 came out like 2 days ago, apparently.
Yeah.
Did they put the headphone jack back or no?
Probably.
That's stupid as hell. So you go from the deli back to the electronics store. Okay, so now you're back in the electronics store getting those headphones or that adapter you hate to pay for. And then finally you walk to the subway station to take a train downtown. And where are you walking from? Well, you're walking from the electronics store. You can't teleport. So you've never gone back to the office. You're playing hooky this day pretty much, right? You go to the subway, and you end up at the subway, and you get on the subway to go downtown. But you know what? When does the problem end? Does it end when you're downtown? According to the wording, when does the problem end? When does it end? When does it end? At the subway station. So let's denote our starting and final position then. This is x0. This is x. Does that make sense what I'm saying? From beginning to end. So what is my overall displacement, people? This is the easier part of the problem, obviously. What's my overall displacement in this problem? What would I get as a value here? I'm seeing the same hands all the time. What am I getting? Julie, go ahead.
Positive 120.
Positive 120. Very good. And again, I get that because I take my final or current position and subtract my initial position. 140 minus 20 is 120. So my displacement, x, is going to be, again, 140 minus 20, which equals 120 in the units of meters. So there's my displacement for this problem. But the other part I got to get still is the distance traveled. Distance traveled. So it's very easy to do it by just adding numbers together right now. I'm going to write down some symbols that would help you going forward and also next year when you're in AP Physics and Calculus. So here's how I would calculate the distance. I would say first that the distance, I'm going to use the other side of the screen over here, that the distance is equal to the following. It's equal to the sum of all of my displacements from, and this is the hard part, it's hard to use the symbols because I'm not using the subscripts the way you would in calc, but from, let's say, part 1 to part 4. And the symbols look weird right now. Don't worry, because you're going to learn these in pre-calculus. I'm trying to give you guys like little head starts. This is a summation, and because there are 4 parts to this problem, I'm going to put a little I subscript on the outside here, indicating that I'm going to sum together this number 4 times, once for each part. Why am I putting absolute value? Why am I putting absolute value?
If you have negative motion, then it's subtracting, but really you're moving further, so it should be more.
See what she's saying? Like if I walk this way 10 meters and then come back 3 meters, what's my distance traveled? 13 meters. 10 plus the 3 back. But my displacement would be 10 minus or plus a negative 3 if I did displacement. Is that clear? Displacement direction matters. So for distance, my values I need to sum together are these vectors drawn in the 4 colors. But if I look at the blue or the yellow one, it looks like those vectors are negatives, right? But really, I need to recognize that if I'm looking at distance, I need to take the absolute value. So really, my distance traveled here, again, is going to be the sum of these 4 paths taken. Oops, I don't need another plus sign. So I'm going to fill in those blanks now. But again, the distance is the sum, that's this symbol here, summation. I equals 1 to 4 means from the first motion to the 4th motion. That's why the I is that little subscript down here, indicating that it's going to change how many times you add this together. Well, let's take a look at my first motion. My first motion would be 280 minus 20. And where is that coming from? Where's the 280 minus 20 coming from in the first bracket there, Isabella?
Well, it's from the office electronics work, but like you have to know that you have to minus 20 because the office starts at 20. You can just leave it at 280.
Yeah, so this is like my final position at the end of part 1, right? This is how many parts again? There are 4 parts to this problem. That's my final position, that's my initial. So final minus initial gives me delta. So 280 minus 20 gives me the overall displacement, which is 260. I put absolute value, so I guarantee that's a positive number. How about my second motion along the blue line, Seb? Technically, thank you, very good. It's technically 240 minus 280, but it's inside the absolute value. Again, it's the second segment. My final position along the second segment is right here, which is 240. My initial position along the second segment is at 280. So it's final minus initial. So 240 minus 280. But because it's distance traveled, I want the magnitude of that, not the direction. I want only the value. And the value is indeed 40. Okay? The third vector along the green path, Jackie?
280 minus 240.
Yeah. 280 minus 240. This is the opposite of that one. Very good. 280 minus 240. Because my initial is 240, my final is 280. Final minus initial, 280 minus 240. And last but not least,
140 minus 280.
we have 140 minus 280. 140 minus 280. And why is it 140 minus 280 again? Or 280 minus 140? How come, Justin? So your hand up also?
Because 140 is the final position.
Good. 140 is the final position, and it's always final minus initial. So what we end up getting here is going to be what? 260, 40, 40, 140, 4 and change. What do we got? 480, I think? Yeah. 480 meters. So pretty much that day you walked about a quarter of a mile. Quarter of a mile. Good numbers to know, by the way. Maybe jot that one down. Anybody know miles in meters? 1,600 meters. Anybody that runs track cross country probably knows that one. The 1,600 meter competition. Or is it a 1,500 meter in track, or what is the track?
They usually have 15.
It is a 1,500, you see? Okay.
16, and then for the girls it's 14.
Is that really what it is? So the boys race a mile, while the girls race 1,500 meters.
I know, it's weird.
It's weird. It's not like they're competing against each other or anything.
It's just they make the girls run last.
It's
It's
stupid.
like that for a bunch of other reasons.
Really?
It's like tennis, how they have women play like 3 sets and men play like 5 or something.
Is that right?
Or like the boys.
It's kind of messed up.
The boys also have the 32.
You should start a platform about that. That's pretty messed up. Yeah. Let's move on to the next problem, or the next topic. So, average velocity. Pretty much what we did with the motion detector lab the other day. Average velocity. Let's talk about this. So, average velocity, by definition, is the displacement of an object over a given time interval. And the formula is written just that way. Anybody ever seen the line over a variable before? A line over a variable? Maybe, maybe not. If you ever did anything with statistics, maybe in middle school, I was thinking of it.
I had a calculator when finding like the mean, it's X.
Yeah, very good. The mean. The mean in statistics, and mean means average. Okay? So when you see a little bar over something, it means average. If you didn't know that, you should probably write it down. Okay? Because that's going to happen throughout the year. So a little bar over something means average. You see it in statistics also if you take AP Stats next year. Now, with that said, let's take a look at the first example, because there's really not much more I can give you on this besides the formula for now. By the way, what is in bold on the right there? I didn't discuss it in the last formula. What's in bold on the right? What's always going to be there pretty much, George?
The units.
The units, okay? When I put something in bold in brackets, I'm referring to the units in that problem. So the last formula was delta x, and m was in brackets standing for meters, okay, for meters, not for miles, obviously. Let's look at example 3. During a drag race, and a drag race, by the way, is where there's no turns. It's a straightaway. So your book refers to drag races a lot. You need to know that it's only one dimension. You're not turning the car ever in a drag race. Fast and Furious, have you seen the originals? The drag race novels? So during a drag race, no turns on level ground, Jamie drives her go-kart, go-kart drag race, her go-kart with an average velocity of 6 meters per second. How fast is 6 meters per second? It's 6 times faster than this. This is one, remember I talked about 1 meter per second? 1 meter per second are big steps. So a big step is about 1 meter per second. So 6 times faster than that. So you have a number sense of what you're qualitatively looking at. What is her go-kart's displacement in meters after 2 minutes and 17 seconds have elapsed? What is her go-kart's displacement? So this is what I was talking about for the problem set format. Here's how I want you to do format all year. Yeah, this is an easy problem. I know it is. A lot of you are like, I can figure it out in my head problem. But the format I want you to use all year is as follows. Start by listing the givens. So we're going to do this with the right format together today. And then going forward, you're going to have to pick and choose when you want to adjust your format accordingly. So what is given in this problem? What values are given?
Time and velocity.
Very good. And it's average velocity in this. Oh, actually, does it say? Yeah, average velocity, which is different than just saying velocity. Let's keep that in mind. So those values are given. Time is 2 minutes, 17 seconds, and the average velocity is 6 meters per second. East. What are you thinking? East.
Going to the right.
Good, which means it is?
East.
Therefore, the sign on the velocity is? Positive. Very good. If I said west? Negative. If I say north?
Positive.
South?
Negative.
Okay? Know those directions, please. Okay. Now, those are the two values I have. Can I go right into my formula? Can I use my formula v bar equals x over t right away to get x, or delta x rather? Can I do it right away, Maura?
No, because it's the unit is 60 per second, and you have unit 10 seconds.
Very good. The units don't agree. If your velocity is in kilometers per hour, then your time has to be in hours. If your velocity is in angstroms per minute, then your time has to be in minutes. Our velocity is meters per second. So our time lapse needs to be in seconds only. So let's convert. 2 minutes, how many seconds is that? This is one of those times where you're not going to write out your word for converting. You could, but if you don't know that 2 minutes is how many seconds, then you probably don't belong in this class, to be honest. I'm not trying to be mean, I'm being honest though. You should know that 60 seconds are a minute, and if it's 2 minutes, it's 120 seconds. So this value is 120 plus 17 seconds, or simply 137 seconds. So right away, convert your units if you have to. Again, when necessary, show the conversion. When it's simple, do it in your head or in your calculator. Okay? Now, at this point, we can go ahead and start our formula. Well, let's look at what's desired. I call this the desired variable, or the variable that you're seeking. Whatever you want to call it, you can call it. But the desired variable is the go-kart's displacement. What variable is that? More specifically, not just x? Delta x. Delta x. Because x would be the position at a given moment. So we go ahead and look at our formula next. What formula involves these three variables? This is how we're going to approach all of physics this year, by the way. You're going to have, if you recognize already on your formula sheet, a ton of formulas, right? You notice that? There's a lot of them on there. Well, you need to look at the variables given and say to yourself, what formula involves these three variables? Or at least these three variables. And what's the only formula we know, Jack?
Speed equals distance divided by time.
No, what's the formula we just used? We're looking for displacement, and we talked about velocity, so use different words, Jack.
Oh, that's what you, okay.
Yeah.
Change in the displacement one?
Yep.
So x minus.
No, sorry. Help me out. You're just using the wrong terminology, Vin.
Average velocity equals delta x over delta t.
Good. So, in a moment, Jack, we're going to talk about speed and distance and time being very different than velocity. So I don't want to confuse anyone and use the wrong terminology here. So we are not referring to speed and distance in this problem at all. We're going to see that in a moment when we get to those problems. So right now we're referring to average velocity, and we're referring to what we call displacement, as the words were shown in the question. So we need to figure out the displacement. So this is what I mean by generic solution now. A generic solution in physics involves no numbers. It means solve for the variable of interest. What's the variable of interest in this problem again? What is it, Seb? Delta x. So Caroline, if I solve for delta x, what do I get in the equation?
So you're gonna have delta t times the average variable equals
Average velocity. Very good. Very good. It's all right. Average velocity times delta x, times delta t, is our delta x. How do I get that? I just solved this equation. Think of delta t as a number. If you were taking your variable of interest, for those that are struggling with this is why you had you do your summer packet, by the way. If I think of this problem as this, think of it like this. And these are not the right numbers. These are not the numbers for this problem at all. Okay, that's how you would approach this kind of a problem. How would you solve this for delta x? Whenever you're stuck, put numbers in for the variables that are not of interest in your mind. How would you do it? You would multiply by 5, and this would become 5 times 10. So you're going to multiply out by delta t. So it's delta t times v bar. I write it as v bar times delta t. Okay? And now, your final step in all problems is to plug in the actual givens. You might be saying right now, Mr. Howell, you're freaking nuts. I could do this faster if I plug in numbers earlier. I don't have to worry about this generic solution crap that you're telling me about. Trust me for now, please. As we get to more difficult problems, this methodology will become very useful and powerful because I can vary things very slightly and I can change my result.
Should we show how we found delta t? Because we were going to start at 0, right? I'm still
I like you, Vin. Very good. So Vin's right. Technically, I should write 137 minus 0 for delta t. Very good, Vin. Because what time did this problem start at? If we don't give a time to start at, we assume the start at time equals 0. Very good, Vin. Some problems throughout the year will denote that a problem starts 5 seconds in, where you start calculating your data or recording data 5 seconds in. So you have a coordinate of t equals 5 and a displacement or position of 10, and a t equals 7 and a position of 12. And then your delta t you have to subtract. So a very good point, Vin. It should be 137 minus 0. Minus 0. Now our answer for delta x is not x or x0, it is delta x. The answer we get here, and that gives us 822. And my answer is definitely positive because my velocity was positive. So I don't know if I started at 0 and ended at 822, or started at 100 and ended at 922. Or started at 200 and ended at 1022. Does everybody follow what I'm getting at by saying this multiple times? This is only my net displacement. It is not my starting and ending point. So again, this problem, although written as if it's a starting line because it's a drag race, I could think of this problem as the following. I could think of this problem as starting at 0 and ending at 8 not drawn to scale, figure not drawn to scale, and ending at 822. I could draw this problem as starting at 100 and ending at 922. I could draw this figure as starting at 200 and ending at 1022. You follow what I mean? All I know is that my displacement was 822, 822, 822. But it could be any of those three vectors in motion. I could start at 0, I could start at 100, I could start at 7, I could start at 12. I could start at negative 2,000 and then add 822 to that, and we'll see where I end up. So again, delta x is your displacement. It doesn't tell us where you start and end. It just tells us how much you've covered from beginning to end. From beginning to end. All right. Can we go to example 4? Yeah, let's keep moving. So example 4 says the following two students walk in the same direction along the straight path at constant velocities. This whole section is going to be these kind of problems. One of them is at 1.5 meters per second. The other is at 2 meters per second. Assuming they start at the same point at the same time, how much sooner does the fast student arrive at a destination 500 meters away? So, we can do this problem two ways. Can anybody foresee the two ways we can do it already? There are 2 ways to do this problem. Give me one of them.
The first way is using just regular math.
First way, just using regular math. What do you mean by that, Regina?
Like, so you would take the distance and divide by the velocity.
Yeah, so you could do it twice. You could do it for the slower person. You could do it for the faster person. You'll get 2 times as answers, right? And then what are you going to do with those answers? Subtract them to see how much quicker one got than the other. That works. That definitely works. Want to stick with that for now? Let's start with that. Let's see if anybody picks up another idea. So let's say object or student or person number 1 is moving with a velocity on average of 1.5 meters per second. The second person's average velocity is 2 meters per second. They both move the same distance because they're running the same race or walking the same race. I don't know if I'm starting at 0 and ending at 500, but I know delta x is surely 500. Okay, I could be going from, again, 0 to 500, or 100 to 600, or 200 to 700. But I know that delta x is that number. So in both problems, I'm searching for delta t. Notice I don't write the words given and desired variable anymore. So I wrote it on the first example. I'm not going to waste time writing those words every time, but the structure is in my head. It's literally ingrained from taking physics in high school, studying engineering, teaching physics for the last 11 years. So it's ingrained. It's not going to be ingrained in your head today, but hopefully soon it will be ingrained that you always start with given, desired, then formula. So here's my given, here's my desired. And I should denote my desired with different subscripts because they're going to be different. So my desired should have subscripts. Delta T1, delta T2. Why is delta X not given with a 1 and a 2? Why is it not given? Because they're the same. If I tell you the mass of one object is the same as the mass of the other object, you can call them both M instead of calling them M1 and M2. It's when things are different that we denote with the subscript to indicate the differences. The formula being, again, V bar equals delta X over delta T. V bar equals delta X over delta T. My solution in terms of variables for delta T, this is one that happens all the time, by the way. This one shows up all the time. How did I get that generic solution so quickly? What operations did I perform? How did I get those so quickly? What's the quick way of getting delta T by itself? What am I doing with this formula here?
Just dividing it and you're switching places of delta velocity and delta T.
Very good. Recognize here. Guys, this is just division. So really you're going to eventually divide by V, but you're going to multiply by T. So what are you just doing with these two variables? You're just switching. Whenever you have a formula that's triangular in nature, where you have a numerator and denominator, you can always switch diagonally. It's a proportion. When you were in like 4th grade, you learned this thing that you were like, I'm never going to use this. And it stated the product of the means equals the product of the extremes. And it's like a really old thing. And here's what it means. It simply means that I can cross multiply and set them equal. But I can also cross change my positions. So whenever you get a triangular formula and you're looking for something that's in the denominator, simply move it up here and switch it with what's up here. So those two switched. Okay, so I multiply by t and divide by v. So what do we get in these problems? We have 500 over 1.5, and this is in meters, and this is in meters per second. And the second one is 500 over 2. 500 over 2 is 250, that's easy, and that's in seconds. And 500 over 1.5, what am I going to get? 333.3. And that's going to be repeating. Are those my answers, though? They're not my final answers. What's my final answer in this problem?
The difference between the two.
The difference between the two. Okay, delta T1 minus delta T2 is going to be 83 seconds. 83.3 seconds ahead. 83.3 seconds ahead. All right, I'm going to leave it like that for now. I'm not going to jump into that and get ahead because I don't want to confuse anyone or get ahead of myself. So a problem like this has two parts to it. Those parts are coupled. When I say coupled, it means they're used together. A problem where the parts are uncoupled is they're not related to each other. It's like part A, part B, part C that don't affect each other at all. But these two parts of the problem affect our final answer. So we would say that they are coupled. Coupled. A good word you're going to use a lot if you study engineering. Yeah.
Would the other way be to use like 0.5 meters per second as the difference, as the average velocity of the difference of it? So you don't need to do it once.
What would you get if you did that?
Probably the same answer. Oh no, you would get the difference right away.
You have a right idea. So Morrow's talking about relative velocities of the two objects to see a gap changing. It's more applicable for problems where we're trying to figure out, like, how long will it take to catch up to the other object? Or how long were they closing the gap when two trains are heading toward each other? That's when the difference in velocities is more useful. Because here, the difference in velocities would be 0.5, right? And then where would I utilize that, Morrow? How would I end up getting 83.3? Think about it as we're doing the next part of the problem. Just think about it mentally, and I want you to recognize that it probably wouldn't be as applicable here as it would to a later problem. That's why I stopped to not say that, okay? But good idea. I like the idea. Velocity versus speed. Let's get into this. So velocity we already talked about, right? Velocity is delta x over delta t. Speed is going to be distance over delta t. Average speed is your distance traveled over delta t. So d will denote distance and delta x will denote displacement. Well, you can see that this is analogous to the velocity formula that we spoke about a moment ago, again, which is this. So depending on the problem, we are going to use a different formula. So when I'm asking about speed for a problem, we need to use the overall distance traveled over time. So let's give a conceptual question. You leave New York today and you go to drive somewhere. I don't know, you're visiting a college up in Boston. How many people have been to Boston at some point in their life, or the Boston area? Okay. So you know if you've driven there, can you drive directly to Boston? Like straight line directly to Boston? Obviously not. From New York City at least, or from Long Island. So you have two options. You go to Long Island, you get on the ferry, take the ferry across with your car. That's a pretty cool ferry I've never done before with a car. You get off with your car, and you drive to Boston. Or you drive from the city, kind of around, into Boston. Right? So when I ask you the following, tell me how fast you were moving on average during the trip. Tell me how fast you were moving on average during the trip. When I ask that kind of a question, physically, am I asking about your average speed or your average velocity? Which of those, that's an X by the way, sorry. Which of those do you think I'm referring to when I ask you about your average speed or your average velocity? Which am I referring to here? When I say how fast you're moving. Vinny, what do you think? Why do you think it's speed, Vin?
Because you're not going straight for because using displacement when you're going straight to it, that's all.
Yeah, you're not physically going straight there. So you can't use your displacement really. That would be giving your average velocity, which takes into account the curvature. So let's draw this path. So here's New York. Let's say the path you take is up I-95, then around. You have to go a little bit down, then come back up into Boston, and then you end up at South Station. From there to there, the black line drawn is your distance traveled, where the red line drawn is your displacement. So when you're asked to find your average speed in the problem, it matters how far you physically go on the curved path. So when you're trying to find how fast you're going on a trip, you're always regarding or referring to your average speed, unless asked elsewise. Unless the problem directly says, what is your average velocity? And then you would use this length of delta x divided by your time period. But if a problem simply says, at what average rate were you driving? Like what average rate would your speedometer show? That's the average speed you found using distance, not displacement. I saw a hand pop up at some point when I was talking. We good? Okay. Let's look at an example to see this. So a book is moving or is moved on a table around the edges. The table's dimensions are given. If the book ends up at its initial position, what's the displacement? If it completes its motion in a certain time, what is the average velocity? And then finally, what is the average speed? So this is a very easy problem, and the reason I say it's easy is because there's not actually much math needed here. So what is the average what is the overall displacement of this textbook if it again ends up at its initial position? What do you think, Nick?
No displacement.
No displacement, very good. Okay, and again, why is that? Because it's final minus initial position. And if I need a diagram, here's my diagram. My initial position, starting in the bottom left corner, equals my final position, x. So when I use my formula for delta x, which is x minus x0, if those values are the same, it must equal 0. It must equal 0. Now, the path taken, though, is shown with the dotted lines. And if I sum together those four values, what am I getting instead? If I sum together those four dotted lines, I'm getting not the displacement, but the distance. And I'm going to do this twice, right? So I'm going to put times 2. Can everybody bear with me there? I'm going to have to show it 4 times, please. 175, 2.25, 175, 2.25. So I'm doing the width and the length twice, so I'm putting a 2 on the outside. So my total distance traveled in this problem is 8 meters. So I've got my displacement, I've got my distance. I'm now asked to find the average velocity. And then I'm asked to find the average speed. So clearly they're going to be different if I'm asking to find both, right? Or there's a good chance that they have some differentiating characteristic. So my average velocity, if you remember, keep putting delta there. My average velocity is delta x over delta t. But my average speed is going to be my distance over delta t. So my speed is 8 meters over the total 23 seconds, while my velocity is 0 meters over 23 seconds. So although it's not logical to state this, your average velocity is 0. Okay? But it doesn't make sense because you're like, wait, I moved. So how's that possible? So most of the time we talk about things, we're talking about average speed. Average speed, and it's approximately 0.35 meters per second. Okay? Again, the 3 answers that were asked. First were displacement. Second was average velocity. We needed distance to find speed, so I wrote my distance formula down here, and I calculated distance, but I didn't actually ask about it in the question. So those are my 3 answers. So what conclusion can I draw? What conclusion can I draw? Yeah?
That the average velocity is directly affected by the displacement of the object.
Good. While the speed is affected by not the displacement, but the... Good. What else can I draw? Other conclusions. Come on. from a simple example of the conclusions. For any problem, if you take this problem and generalize it. For any problem, if you, what did we do in this? Thank you.
If you end in your starting position, your velocity is already zero.
If you end where you started, your displacement and average velocity net out to be 0. Listen carefully. What I'd like to do is the following.